Good morning, friends. This is Professor a.k.chaubey, Professor Chaubey's Physics Class, under the heading Physics Made Simplest. So, dear friends, today I am going to discuss more AC circuits involving mixed components like resistance, capacitance, and then resistance, inductance, capacitance, etc. And then maybe we'll solve some problem or next time. So, I am today talking about the AC circuit involving R and C in series. So I have a AC source. E0 is the maximum value of this potential. E is the instantaneous value. At any moment, E is equal to E0 sin omega t. Omega is the angular frequency that represents in fact the angle traversed by the vector, maybe electric or potential. R is the resistance connected in series with a switch, and C is the capacitance. So RC in series connected. The E potential or EMF is impressed over this R and C series combinations. Current will flow through this, and current, say, I, instantaneous current, any moment, any instant. So this current flow here gives a potential drop, IR drop here, that is VR, and a potential drop here across condenser, that is VC. You know that this is the I into XC, this is I into R. So this is the situation. And now, say, we go to further discuss, say, we write say, EV. Oh, this is not good. EV as RMS value of voltage, IV RMS value of current, and what else we have, VR, as I told you, is I into R, IR drop. I means, of course, RMS value, and VC is equal to, say, IV into XC, that is the capacitive reactance. VC, lags, VC lags IC, IV by 90 degrees. We know pi by 2. That is, the current is behind. Inductance, VC, potential is behind the IV. Means current is more, current is positive than positive maximum, VC is 0, like that. So VC lags, means condenser potential is behind 90 degrees. While inductance potential, is current lags behind. Potential is more because the back EMF. So we know that EV as a potential vector is VR square plus VC square. This we know from the triangle of the VC and VR, that is the potential EV. And we also know that this means the EV is equal to IV, we can take common outside, and inside we have under root of R square plus XC square. And so IV, so this means that current IV is equal to EV upon Z, that is impedance, equal to that R square plus X C square 1 by 2. So this we know. And we know that, yeah, EB over Z. Z we know this is equal to this. So we know that the current IB and the potential VR are in same phase, no phase difference. VR potential drop and phase, and the current has no phase difference. They are in phase. While we know that across the capacitance, what we have, that potential lags means it is BC lags. So pi by 2 difference, phase difference. Now you can have say this is the potential diagram. We are in same phase as I, and BC is minus pi by 2. This lags behind, and the result of this two is given as the here say IB or B EB. This is the result is EB. EB is equal to this. EB is IB, IR drop, IB into this. And Z is the impedance. The same triangle can be used with a different magnitude, of course. That is impedance triangle means this is the Z, this is the say XC, and this is say R. So you can make separate triangle. I have shown because it will be similar, but its magnitude will be different. Z impedance here and resistance R and capacitive inductance here, XC. So this represents the impedance diagram, represents the voltage diagram, everything. So this current flowing through the RC has got EB over this value, magnitude. But remember that we write the mathematical equation, the phase difference tangent phi. This phi is given by tangent phi phase angle. Tangent phi is given by this over this voltage. So this is simply tangent phi is equal to minus VC over VR, and that is simply XC over XR. This means XR means R simply. XC over R. So this is tangent phi, phase difference phi, given by the ratio of the voltages. And power consumed, so if it is only capacitance, the phase difference of the VC and I is 90, but it is now mixture R and C, and so phase difference is like this. We start here, say this is the E with omega t x-axis, and this the here it may be maximum, say E naught amplitude, I naught amplitude. Then this is the phase difference, means current and the potential or EMF. Current, because due to the opposition of the capacitor, it is also resistance, capacitive resistance, or it is called reactance. That current has got a phase difference, the potential, that is this much difference, this much angle. This angle I have written phi. So that is the current lags behind, means capacitance will not allow current immediately to be maximum. If current here is 0, at that time current, because if the BC the capacitor is charged, when this potential becomes 0, current, this starts sending the current, means discharging. So that current is this value. When this is full value, means it is charging is stopped. Potential of capacitance is maximum, it is fully charged, and then current is stopped. So when this becomes maximum, of current becomes 0. When this is say here 0, potential, this is maximum, opposite charge. Because current becomes zero, it is fully charged. So this diagram represents, you can say, phase diagram of the potential and the current. This is the current I and this is the potential. This is the y-axis showing both potential and current, and this is the plus side, this is the minus side. You can say this is the plus side, this is the minus side. So for half cycle positive, half cycle negative. So this is the phase difference, the same phase difference, phi. Phi is the phase difference between the voltage and the current. Means voltage of RC circuit. Remember, voltage of only capacitor lags behind the current. Voltage of RC combined circuit here leading by, say, this phase difference phi, current is lagging behind by this phase difference phi, where phi is given by ratio of the capacitive inductance, the capacitive reactance divided by the resistance. And the power consumed you can write, well, power consumed, that E is equal to E naught sin omega t, and so E, is E naught. E naught is from RMS value, that is under root 2 EV, RMS value EV. RMS value EV is maximum E naught by root 2. And I is equal to I naught sin omega t plus phi phase difference, where I naught is equal to, just like this, under root 2 of IV RMS value. And average power consumed, average power consumed. Will be equal to EI and that is EI means EI, E and I. So this E naught under root 2 EB, under root 2, so this will be 2. And EB, IB cos phi. EB, IB cos phi. So here, average means you have integrated the sign, that factor will be 0, and we will have this. As we have earlier done with the inductance resistance case, same thing here. It will be EB, IB cos phi. And that is P is equal to power in R plus power in C, and that is IB square R, and this is 0, capacitance, average, because half cycle plus, half cycle minus. So this is the power is simply IB square R, because resistance is there. If only capacitance is there, only inductance is there, average power is 0, because for half cycle it is positive power, for half cycle it is negative, means power is stored. For negative cycle it is power is given, so total power becomes 0. But because R is included, so that is not 0, it becomes IB square R. I think now I can rub this circuit diagram also, because all this I have already talked about, this triangle and phase difference, everything. this so I can clear this. And now what we can have. So I want to solve say a problem, or I will solve problem maybe in the end when I discuss all the circuits. Now I talk about R, L, C circuit. RLC circuit. Now we have a circuit involving say R, L and C. What that? That means inductance and resistance and capacitance, all the three together. So that is a R and C. So what will be that R and C? Now we have say a circuit R, L, C, R, L and C. We put a key just circuit breaker, and E is E naught sine omega t. There is a circuit. Here we have this involves now a potential drop across resistance. This has a potential drop across inductance, and this has potential drop across capacitance 3, and this is E equal to E naught sine omega t. So our RMS value is E, average value is EV, and this is the current IV or I or IB is the average value. This circuit and RLC in series. So what we have, this is general series circuit. This is a general RLC series circuit. Series circuit across supply, across AC supply, the potential, average potential EV, or E is equal to E naught sine omega t. And this gives EB and IB are average or RMS value of potential and current. Now what we do? The voltage across R is VR. Yeah, this is VR equal to IVR, that is the RMS value of the current. This is in phase with IV, and voltage across C or L, voltage across L is VL equal to, say, IV into XL. We know XL is omega L. VL leads IV. This leads IB by pi by 2. And then voltage across C is VC equal to IV XC, and this VC lags IB by, this lags IB by pi by 2. Means this is plus, this is minus. So these are the results we know already from previous discussions, and we can make, say, voltage diagram, or we can make impedance diagram, vector diagram also, that we have done in earlier cases. Here we can draw, say, 0 here, and this is a VR, and here VL BL pi by 2 plus, and then here we have say what we call, say, this is the time scale, or you can say current IV. VC is down by pi by 2, that is 90 degrees. So this represents a down, so that is a VC. So VC is, say, this much amount, this is the VC value. So here VL is, we can assume VL more or VC more. It depends upon the value of L and C. So I have assumed, say, VL is larger than VC. So this is the result is here. That is VL minus VC. From this we subtract this. This is left, means resultant. And then we join this point here, so that we have this O, this is the A point, and say D point, you can say D point here. And so this value was VL, this value is VC, on this axis you can say negative axis. So this is VC. So that is VL minus VC on this side. So this becomes a resultant, and that is the EV. EV, the RMS value, is now depending on this VL minus. It can be VL minus VC or VC minus VL. So EV is equal to, now it is a vector sum of, because this is 5 degree here, but these two are 90 degree here. So this vector VR square plus VL minus VC square under root. This gives the value of EV. Or EV is equal to VR is IVR. So IV square R square plus VL minus VC. This is IV square, and this is XL square XL, of course, minus XC, this square, and this is under root, so 1 by 2. So this gives you the value of EV. EV is like this. So IV we can take outside. So EV is equal to IV outside, and then R square plus XL minus XC square, and this is 1 by 2. So this is an impedance, you know, so EV or IV is equal to EV divided by, say this, EV upon R square plus XL minus XC square, and then 1 by 2. So this represents, just like current is voltage upon resistance. So this is the impedance of the circuit, Z is equal to R square plus XL minus XC square, and then 1 by 2. So this represents impedance of the circuit. So you can make impedance triangle also, where this will be the Z and this will be the XL minus XC, this will be the R. So impedance triangle also can be like this. So that is the Z impedance, this is the R, and this is the XL minus XC. So this becomes the impedance triangle, this is the voltage triangle, the circuit, and so impedance Z is like this. So this is the RLC circuit. So now you can see that it depends upon XL and XC value, that is the VL and VC value, which is more. So that will be more, so you can have XC minus XL or XL minus XC. So that is a circuit current IV and supply voltage EV are in phase. Circuit current IV and voltage EV are in phase, having phase such that tan phi phi, phase phi, that gives you the from the triangle, that is that you can see. Well, we can have, say, here, if XL minus XC is positive, that is XL is more than XC, the angle phi is positive. Angle phi will be in the positive side because upper half, the angle phi is positive. And the circuit will be inductive because XL is more. Inductive. Good. I will lag behind the supply voltage EV. IV will lag behind the voltage by phi. That phi you can calculate simply the ratio of the perpendicular to the base. That is the phi. That is tangent phi, of course, is, tangent phi is xl minus xc divided by r. This is the tangent phi. Because it is the voltage. Voltage is simply IV into this, IV into this. So that is the voltage ratio. So that is the impedance, or you can have impedance triangle. So tangent phi is given by this. So if XL is more than XC, in this case the phi is positive. Phi positive means IV will be behind the current, will be behind the voltage. That is the inductance is more important here. Inductance is large. So that is the opposition. Back EMF is more. So that is the circuit will oppose the growth of current, and IV will lag behind. And you can have, if XL is less than XC, means capacitive inductance is more than inductive reactance. If this is the case, XL is less than XL is that is XL is less, or XC is more than XL. This thing, XC is more, then it will be minus. So then what you can say, the circuit current IB will lead the voltage EB. Here it was lagging by 5. That inductance is less, so back EMF will be less. So that will be, means XC will be more. Then the current IB will be, I will lead. Here current is lagging, here current is leading. So these are the cases. And if XL is equal to XC, third case can be XL is equal to XC, means this part vanishes, means Z equal to R, only impedance, and we have say EV and IV have no phase difference. They are in phase. In phase. They are in phase. So then this means phi is equal to 0. No phi. Then here power factor. Power factor is given by tangent phi. EI, E into I into tangent phi, cos phi, EI cos phi power. So that is power factor. Power factor is 1. Phi equal to 0, cos phi is equal to cos 0 equal to 1. Because that power, EI cos phi, that is the EV, IV, average. So power. So this means cos phi is equal to 1. This case, then that is power factor is 1. Phi is equal to 0. When this is the case, then power factor is 0. So this is the, we have discussed the inductance circuit, capacitance circuit, capacitance and inductance circuit, capacitance, resistance circuit, etc., etc. Now I think friends, I can stop here, and maybe next turn we may discuss some problems based on all these circuits, some numerical problems or some other type of problems. So friends, thank you very much for listening to me.